don't know what's going on, have a graphic protocol. And what that means is essentially it's an agreed handshake and message structure for communicating over a network. And the whole point really of TLS is that that communication will be encrypted and authenticated. And that means that you won't be able to read the messages if you're an attacker. And also, no one can pretend to be the other person on the other end of the line. So, for example, you're a robuster man in the middle attacks, or imposter servers who are pretending to be Amazon and steal your credit card details or something like this. That's kind of the idea. It was mostly produced because of the web and the need for encryption on the web. But nowadays, TLS is very commonly used elsewhere as well. So it does a few specific things. So we try and agree cryptographic parameters. So what secret key are we going to use? What cipher are we going to use? How long is our key going to be? These kind of decisions. You have to make those decisions, because if you don't, there's a very good chance that you and the person on the other end of the line will be talking a completely different set of algorithms, and they won't be compatible, right? Unless you're using the exact same key and the exact same algorithms, you're not going to be able to read and write those messages. It also will authenticate identity. So it will check the identity of a server specifically against a certificate, which you hopefully have some sort of trust in. And we'll also talk about public key infrastructure a little later as well, which is how we do these digital certificates. And then, of course, we actually transmit messages. So there is a standard way inside TLS to send message data back and forth. It's currently at version 1.3. Version 1.2 is still very, very common. Right? I would expect your browser will almost certainly be using 1.2. It might be using 1.3. I think mine's using 1.2 at the moment. I've clicked more information and it's using TLS 1.2. Right. So although we've moved to 1.3, 1.2 is slightly more widely used, I think, at the moment, probably mostly for compatibility reasons, and maybe people are a bit slow updating. But either is fine. And like I say, it's used a lot for HTTPS, but that's not what we're focusing on today. We're mostly talking about the protocol, and what you send within the protocol is really up to you. Right? So it could be any kind of data you like. Okay, so how did TLS come about? Well, the first thing that's worth mentioning is that transport layer security was not always what this was called. Right? So a lot of you might refer to this as SSL, or secure sockets layer. And the reason for that is because that's what it used to be called. So in November 1994, Netscape, or who made the Navigator browser back then, right? If you're old enough like me to remember this, although 1994 was pushing it for me a little bit, I was not that old. Maybe I'm lying, I don't know. So they developed SSL1 with the idea of encrypting internet communications. Now, it wasn't very good, right, SSL1, but it was a step in the right direction, and they very quickly iterated this into SSL2. And it looked like there was something good here. And the idea was that websites, your browser, like Netscape Navigator or Internet Explorer or something like this, would be able to form a secure communication with the web server. And that way the website was then encrypted. And you could do things like e-commerce much more securely. In March 1995, Netscape actually deployed SSL2 in Netscape Navigator 1.1. So this was the first actual use of encryption on the web in this way. Now, shortly after this, they found quite a lot of problems and released SSL3. Now, SSL3 was a completely new design of protocol and bears quite similar resemblance to what we see now in TLS, with a fair few more security holes, but it was a step in the right direction again. At this time, Microsoft was also working on a comparable technology, and it kind of became obvious that if everyone was just working on a different form of encryption, then no one would ever be able to communicate. And so it was probably in the best interest of both companies and the web as a whole to work together on these things. So the TLS working group was established in 1996, followed by quite a lot of work, and then the release of TLS1, or Transport Layer Security 1, in 1999. Now, you might be wondering why TLS was renamed from SSL, and the answer literally is because Microsoft asked for it to be renamed because they didn't like Netscape having named it. That was pretty petty, right? That's the actual answer. Microsoft wanted to contribute to the naming because they felt it was important, and so it got renamed for no other reason than that. If those of you that remember the 90s will know that Microsoft were, pushing Internet Explorer pretty hard, and there was what we call the browser wars. So there was a lot of animosity between some of these companies at that time. Now, but as it happens, TLS1 is very, very similar to SSL3. Right? It's got some minor tweaks and some minor security improvements. So actually, TLS1 is, in some sense, SSL 3.1. And you'll see this in the version numbers that go in the header of TLS packets. So they are the same thing. SSL and TLS are the same thing, except to say that TLS is the more recent version. Right? So that makes some sense. The reason why we only ever talk about SSL in code is because it would be a hugely breaking change to rename all your libraries from SSL to TLS. So we don't bother to do that. That's why you still use SSL when you're running code. So, for example, you import the SSL library in Python, right? Not the TLS library. So after this, some time goes by, we introduce extensions, which I'll talk about a little bit later, but small bits in the header information of TLS packets that can add information. And then we get TLS 1.1, which is a security fix, basically, against certain issues with TLS. We then get TLS 1.2 in August 2008. And you can see, actually, I'm still using TLS 1.2 today in this browser session. So it's not deprecated yet. TLS 1.2 is fine, and it's now getting quite old, right? So it's at this point quite a robust protocol, depending on, as long as your cipher you're using is good. Some time goes by, SSL 2 and 3 get officially deprecated around 2014 to 2016. And then finally we see in 2018, TLS 1.3. And not a huge amount else has happened since then. So that's where we are. AP's asking in the Q&A, what was the driving factor for the need for encryption on the web? Was it the advent of e-commerce or something else? I think to an extent it was the advent of e-commerce. I think perhaps also, reading between the lines a bit, the security researchers at Netscape almost felt, shall we say, compelled to offer encryption as a service to the customers in some sense, because they felt that would be a good thing to benefit the customers. Right? So I think it was, there's lots of people that think encryption is inherently a good thing to strive towards, and so have been pushing that for many years. Right? But there are some obvious passwords, credit card information, this kind of stuff, which you just can't really get the web to work properly if you don't have SSL. Right? That's kind of a driving factor. Anyone else knows anything else? Do let me know. Okay, so we're going to talk now about the TLS protocol itself, and hopefully by doing so, answer a few questions about how it is that it works. That's the idea. Now, I'm going to talk about TLS 1.2 first, and the reason I'm going to do that is because I think that 1.2 is a more intuitive protocol, and then 1.3 makes more sense if you look at it, should we say, about what changed from 1.2 to 1.3. If you just present 1.3, there's a lot of weird compatibility stuff in there that gets a bit confusing. So we'll talk mostly about 1.2, and then I'll draw attention to the key differences with 1.3. But by which time you'll definitely know how TLS works. Right, so at its heart, all TLS packets are sent using a record protocol. Right? The record protocol is the name for any message sent in TLS, right? And it contains a header and then some payload data. Right? Now, that payload data may or may not be encrypted, may have subheaders, and so on, but that's basically how a TLS packet is structured. The header contains three items. One is a type of message we're sending, so application data or handshake data or something like this. The version number, so which TLS/SSL version are we using, and the length, which is the length of the payload. And that's because partly it's just good practice to send the length, but also because it's often the case where you might send multiple TLS records in the same packet. Right? And the reason you do that is simply because there's a lot of latency on the web, and that would waste some time if you didn't do that. So the type will be one of the numbers 20, 21, 22, and 23, and we'll talk through those. The version number is going to be a byte for the major version and a byte for the minor version, and they are with respect to SSL. So TLS1 has a version of 3.1, 1.1 has a version of 3.2, and 1.2 has a version of 3.3, right? Which is very confusing, but that is what it is, right? If you look in Wireshark or something at the packets, you'll see 3.3 for most packets. You actually get 3.3 for a lot of TLS 1.3 packets as well for compatibility reasons. So be aware that they're there. Don't worry too much about which numbers they are. NL's asked, if someone's still using SSL TLS 1.2, will they be able to communicate with someone who's implementing TLS 1.3? So that kind of goes in here with the version number. The answer is yes and no, but it's very, very likely that a server or a client that implemented 1.3 would also implement 1.2, but the protocols are different. And what that means is that you agree at the beginning of the conversation which protocol you're going to use, and then you stick to it. Right? And in fact, I'm going to go into detail on that process. So the answer is they will be able to communicate, but only by both using 1.2. The side that uses 1.3 won't be able to do it. Right. The length of the packet, maximum length of 16 kilobytes. Nothing particularly interesting about that. Just is what it is. All right. There's 4 kinds of messages in TLS, starting with 20, 21, 22, and 23. Right. Now, I can't tell you why they started counting at 20. Maybe for future proofing, I guess. But it's a bit peculiar. There are optional other ones like heartbeat, which is number 1, and things like this, but we don't really talk about those very much. These are the 4 main ones. So what do they do? Well, number 20 is change cipherspec. This means that something's happened, like a handshake or some other information has been received, and we're now going to switch to a different encryption suite. Right? So this is used, for example, at the beginning when you begin encryption, but it's also used later if you change key or you change cipher. The alert mechanism is 21. That's any kind of notification to the other party that they've got a bad certificate or that you're ending the communication, these kind of things. Handshake messages, which are perhaps the most important part. That's how we establish all of our cryptographic parameters. And finally, application data. So once you have your encryption keys and all this other information, you've done your due diligence, then you can just send opaque application data. And by opaque, what I mean is that TLS is not concerned with what's going on inside the application layer at all. So you can send any application data over TLS, and TLS will transfer it without any changes. That's the idea. In practice, in theory anyway. All right, so let's talk about TLS alerts, because I think they're perhaps the most simple of the different messages that you need to understand. So they have 2 values. One is a level of the severity of the alert, and one is a description. So, for example, the level can only be one of 2 different values. Either it's a warning, which is a 1, or it's a fatal error, in which case it's a 2. And then the description will be some numerical value that tells you what the error is or what the message is. So, for example, a closed notification has a value of 0, and a bad certificate has a value of 42. Now, the important thing to know about these is, or the important thing to note is that they aren't text. There's no stack trace or informative error message or line where the error occurred or anything like this. It's literally just a number that tells you the broad category of error, right, or the broad category of alert, which is unbelievably unhelpful, in my opinion. So that means that you don't often find out what's wrong with an SSL. I mean, for example, if you get a message that says bad certificate, it won't tell you what's wrong with the certificate. You're going to have to work that out yourself. And so one of the problems with TLS is that it's difficult to debug, because often you'll just get a bad connection and you won't really know what the problem is. Right? I will provide some tips on that at the end. But using something like OpenSSL with verbose mode turned on is much more helpful. You can actually start finding out what's going on under the hood. So here's an example. I just wanted to show an actual example of a TLS message. So there's really nothing that complicated going on. This is a real TLS message that I sent across my network, and I use Wireshark to capture it. It's actually encrypted, which is why it looks like nonsense. But actually, we can break down all the different parts, and you can see what it is that it does. So remember, every message is a record, and the record starts with a header and then the payload. And you can actually read the header here. It's in hex, which is slightly confusing. So this is the record header. Right? 15 is equal to 21, which is alert. Right? 33, that's the TLS version number, so that's TLS 1.2. And then 001A is the length of the remainder of the message. So far, so good. So now we're into the payload. Now, an alert is encrypted, And the fact that it's encrypted, in this case, means there are other additional bits of information that are sent as well. Right? So first of all, you get something called a nonce. A nonce is a number used once, which I talk about in my encryption class. It's essentially a random seed for this particular message. Right? That's all you need. It's not random, actually. It's a counter. But it's essentially a seed for the key stream generator. Right? That's all you really need to know about that. The first message you send would usually have a nonce of 0. The next one was a nonce of 1, and so on as a counter. Then 19.4a is our actual ciphertext. So that's our encrypted message. And then the last bit is actually what we call a tag, or a message authentication code. Now, in this case, I was using AES in Galois counter mode, or AES GCM. And the GCM component of this is the thing that produces that tag. And it's used to make sure that this message hasn't been tampered with or been edited by mistake in transit or anything like this. The key, I mean, the tag is useful from an encryption point of view, and the nonce is useful from an encryption point of view. But from our point of view, what we care about is that C, which is the message. If we decrypt that, we simply get 100, which is a warning and close notify. So this was actually the last message I sent over my TLS session, and it was simply the client saying to the server, that's the end of that, I'm going to not talk anymore. Right? And that was the last message. So it looks complicated, but we've just got a record header and then we've got some encrypted payload. And exactly how that encrypted payload will look might depend on the algorithm you're using to do the encryption. The problem then is, how do we agree on an algorithm to do the encryption? Right? It's all very well me saying, well, I've got this secret key and I'm going to send you an encrypted message. But if I'm using the wrong algorithm, you're not going to know how to decrypt that message. Right? If you don't have the key, you're not going to know how to decrypt the message. Even if your nonce is wrong or your tag is wrong, it's going to be a disaster. So we need a way at the beginning of communication to begin the conversation and then continue on encrypted. That's the idea. And that's what the handshake is for. You'll be familiar with handshakes in other protocols. So, for example, TCP has a brief handshake with 3 messages. SSH has a handshake. IPsec has a handshake. They all have handshakes where they agree what's going to go on from then on. PN has asked, what's the size of C? That's a good question, actually, because I haven't been clear. But in this case, excuse me, in this case, the size of C is 2 bytes, right? Because it's a warning and a close notification, and that's how long an alert is. In practice, you might send application data, in which case your C will be much, much longer because it will be actual data. So, for example, if you're on an HTTPS connection, you might find that your ciphertext is a large HTTP request or an even larger HTTP response or something like this. In this case, you're getting audio over TLS and you're also getting video over TLS. Those will also be encrypted and sent as part of that C. So the only way to work out what the length of C is to take the record, work out how long the payload is, and then work back from there. But because you and the server agree on the cryptographic protocols you're going to use, everyone knows how long everything is. That's the idea. All right. So, so AP is asking a very good question. Is the lack of descriptive errors in TLS because it doesn't want to provide an actual failure reason to attackers? I've never read that that's the case. It's an interesting hypothesis. I don't know is the answer. My guess is that the alert size is because sometimes alerts are not warnings; they're just notifications. So, for example, close notify is not necessarily a fatal error; it's just a warning. And there are some others that get sent in and among the traffic. The fact, to keep size down when internet speeds were not quite as high would be one concern. But then again, you do consider that they could have made these things bigger when they went to TLS 1.3 or TLS 1.4 or what have you. So it's an interesting question. Maybe it is to keep things secure. Bearing in mind, of course, that once encryption has begun, you can't read what the alerts say. So, it is fairly secure. The only thing you do know is how long the message is, and so you might be able to work out that it is an alert rather than other data, but it's not a huge breach, I would say. All right, so how do we agree on all these cryptographic parameters? Well, the first thing is we need to agree on what ciphers we're going to use, so AES, char, what encryption we're going to do. what protocols are we going to use? Are we going to use RSA or DSA? Are we going to use what kind of certificate? And so on. So we need to do all that. And we also need to establish some kind of shared secret material that we can use to derive keys. It's no good doing all this clever protocol if we're using a key that everyone knows because I sent it earlier in the clear. So we need to establish a secret key, and that's very difficult to do. The next thing we need to do is we need to authenticate the server. And what that means is we need to receive a certificate from the server and a digital signature and compare these and make sure that the server is who they say they are. Because if the server is an imposter, that could be a real problem. You don't want to go to a website like amazon.co.uk or something like this, only to find you're actually on an attacker's website who starts, key logging or grabbing credentials or what have you. And finally, and it kind of goes without saying, but I think this is worth saying again, TLS has to be very carefully designed to be robust to tampering and attack. It's very easy on older protocols and protocols people have designed themselves to find some way of circumventing a lot of the security. Right? The reason we're on TLS 1.2 and 1.3 is because all the other ones have huge problems that have been fixed over time. Right? So very, very important not to forget that. That's why it's designed as it is. Sorry, I forgot to mention there's something else on the bottom of my slide before I move on. Each handshake message obviously is number 22. Once you have your record and then your payload, the payload will have a subheader in it. So you'll have your record header, and then you'll have a type and length of your handshake message and the data to do with that handshake message. And you can send multiple handshake messages in the same record. And that's actually what happens because it would be too slow to send them back and forth all the time. Right. So the first thing that happens during a handshake is we have to agree on some kind of cipher suite. Now, a cipher suite is, in this case, just a number or a text string that allows us to quickly work out what both sides will have to do in this conversation. So this is an example of a TLS 1.2 cipher suite. The TLS 1.3 ones are similar. They're a bit shorter. So what this is basically a numerical code, which we're going to look at in text form just to make it easier, that tells the client and the server what algorithms we're going to use, because of course you've got to agree. So it's TLS, and then we're going to use for our key exchange mechanism, elliptic curve, Diffie-Hellman, ephemeral. Now, those of you who aren't familiar with encryption, elliptic curve Diffie-Hellman is what we use to establish a shared secret. So it's a mathematical conversation over a couple of messages that allows you to establish a shared secret key, which is hugely important. So it's a very clever algorithm, and I do, encourage you to look into it more if you don't know how it works. It's very interesting. RSA here is going to be used for authentication or our public key cryptography. So the issue with most of these protocols and elliptic curve Diffie-Hellman is that if a man in the middle is attacking and intercepting your messages, they can rewrite a lot of the data, or they can decrypt things. RSA it means that the client authenticates who the server is, and by doing so can rule out men in the middle attacking. Right, that's the idea. Once we've done the handshake, we're then going to use AES for our symmetric cipher with a 128-bit key and Galois counter mode as our cipher mode. That's the thing that would put that tag on the end of the message. And at various points in the algorithm, we need to use a hash function to derive key material and so on. We're going to use SHA-256 to do that. And that's everything we're going to do. Now, the important thing to understand about TLS is once you know what cipher suite to use, both sides then implicitly know exactly what messages are going to be sent back and forth. Right? And so you can very easily work out if everyone's doing the right thing. If you change RSA for DSA, for example, some things might change. If you change elliptic curve Diffie-Hellman for regular Diffie-Hellman, some messages might change. But once we've agreed on this, the messages are fixed and we know what's going to happen. Okay, so on the right-hand side here is a grayed out sort of transparent TLS 1.2 handshake. Now, I didn't want to show everyone, you can see it's got a lot of stuff in it, so I thought we'd work through it one piece at a time. But as a reminder, so you can kind of, keep in mind what this is for, remember, we need to agree cryptographic protocols, so we want to agree on a cipher suite. We want to establish our shared secret using Diffie-Hellman. We want to authenticate using RSA or DSA. And we want to verify that there's no tampering or attack. Those are the 4 things or broad range of things we're trying to do. This example here specifically is elliptic curve Diffie-Hellman ephemeral with RSA. It only, naming wise, it really doesn't make a lot of difference. Almost all handshakes now are structured in basically the same way. The first thing we do is we send something called a client hello. The client hello is the first message that gets sent. It has its own identifier in the subheader of the handshake. And it includes a few important things. One is the maximum supported TLS version that the client supports. The next one is a random number that they use for initializing random material and essentially making sure that this handshake is not replayed later as an attack. And also a list of supported cipher suites. Right? So that's quite important. So this is a message that says, I'm the client and I can do these different things. So I might support 1.2. I don't support 1.3. I might support AES, but not char-char, and these kind of things. And it gives the server all the information it needs to make a decision as to what they could do, where they both speak the same algorithms. Now, the server will then respond with a server hello, right? No surprises, with the chosen TLS version. So they'll pick one, then a random number again from the server, and then a chosen cipher suite. So this is really, really important. I was asked earlier by NL in the Q&A, can someone who's doing 1.3 talk to 1.2? Well, what will happen here? Suppose the server supports up to 1.3, but they receive a client hello message with only 1.2. That means that the client doesn't support 1.3. Right? So what they would do is they would send their chosen TLS version back as 1.2, and essentially they would downgrade their own protocol from 1.3 down to 1.2. So that's how you can agree. Now, if neither of you support the same, algorithms, that's going to be a problem, right? And you'd get an alert, and that would be the end of the conversation. The server then chooses the cipher suite. So that chooses which symmetric cipher to use, which key they're going to use, the size of the key, what public key algorithms or RSA, for example, they get to choose that. It's worth noting that it's the server that gets to choose these things. You cannot convince a configured server to use a weak encryption algorithm or a weak cipher suite or anything like that, right? Because it's up to the server. It's a good way of doing it, because it means if I turn up on the internet with my extremely old Netscape Navigator browser, servers are well in their rights to tell me to get lost and not bother to have a conversation with me at all. Right? They're not forced to do so, which would make the encryption many times weaker. You see, so that's quite important. SV is asking, I haven't seen this TLS handshake in DevTools. Is there a way to see this handshake? I'm not sure if you can see this handshake within the browser. It usually happens before anything gets sent off, and it's just kind of implicit. The best way to see a TLS handshake is to use Wireshark. I'll just stick the or any kind of packet sniffing software. You can very easily see what's going on, because you can then, it will also parse all the headers for you. It's a bit difficult to understand TLS 1.3 in Wireshark, in my experience, because it's a bit mangled. But TLS 1.2 is really, really good, and you can read out all the values. If there is a way to get to in-depth tools, I've not spotted it. Okay, now the server is going to send us public key certificate to the client. Now I'm going to talk more about public key certificates a little bit later. But the important thing to realize is that this is the identity of the server. It's saying, this is my certificate, but you can verify to make sure I am who I say I am. So at this point, the client will use public key infrastructure to perform certificate verification to make sure it's valid. Now, I'm going to go into a lot more detail in about half an hour's time on that. So I'm not going to talk about it now. I've just written PKI here, so you know that I'm going to get back to it later, right? But that's very important. So the client will look at the certificate and thumbs up or thumbs down, basically. And if it's thumbs down, that's the end of the conversation. The server is now going to send what I think is perhaps the most important message, and that's the server key exchange. So that has the Diffie-Hellman key exchange parameters. These are mathematical parameters to do with the Diffie-Hellman key exchange. They'll also send a public value. So those of you that have done my course on encryption will know how Diffie-Hellman works. The server is Bob in this instance, and is sending Bob's public key over to us. we're Alice, and we're going to be sending our key back to them. They also send something called a digital signature. Now, a digital signature is essentially a small checksum that's been computed using the private key of the server. Right? It's an oversimplification, but that's basically what it does. And the client can use the certificate that they got, which they got some trust in because they checked it, and they can use that to verify the digital signature. So that's another massive part of public key infrastructure that I'm going to talk about in a little while. Assuming that passes, that means the client can be confident in the identity of the server, which on the internet is really, really important. Right. The server then is finished. They send server hello done. And then the client can respond with their key exchange message, where you can see there in grey, there's a certificate and a certificate verify message. Those are used for mutual TLS, which I'll talk about later. That's if you want to authenticate the client as well. So what happens with a key exchange? Well, I've tried to summarize the entire of the incredible world of Diffie-Hellman key exchange into one tiny box. So best of luck. You take the client public value and the server public value that have been sent during the key exchange messages. You combine them mathematically into something we call a pre-master secret. And the important thing is, if I turn on my little pen here, that this is known to only the client and the server. It's not known to anyone else, including anyone that was eavesdropping on the conversation. So that's very, very important. You take the pre-master secret and you combine it with the random values that we exchange during the hello messages, and we get the master secret. And that master secret is what we use to derive AES keys or other keys as necessary. Right? So it's very, very important. And it's also important that it's kept secret. Right, so just bear that in mind. SP's dropped a nice looking link into the chat, so thanks for that. I'll have a look at that in a bit. Although I might need to learn Go. Right. So the next thing is both public key exchange messages have been sent. So now everything is in order, right? The client has verified the server using public key infrastructure, and they've got a shared secret because they've done the key exchange. So they now have all the information they need to begin normal messages, right? So what will happen is the client will send to the server a change cipher spec message that says, I've got all I need, I'm ready to begin encryption. And then they will send what we call a message authentication code calculated over the entire handshake. So basically what will happen is, if I get my pen out again, let's use a yellow pen for this. Think of it like a checksum. The client will take all of these messages and calculate a checksum, and the server will take all of these messages and also calculate a checksum. And those checksums should be the same because they should have seen the same version of events because all those messages have gone back and forth. Right? And so the finished message will contain something that should be identical for both the client and server, and they can be used to verify that no one is tampering with any of the messages. Suppose an attacker edited something inside the client hello, that would mean that the client saw a different client hello than the server did because it had been changed by the time it got there. And so those finished messages would flag this up, right? So it's very, very important that you have these finished messages at the end. And then we're actually finished. That's the end, right? If it seems simple, it's not really, but it's not quite as complicated as people think. The change cipher spec message says, I'm going to begin encryption, and then the finished message is encrypted and contains this summary of all the messages we've seen so far. Right? Now, before I press on, I'll just have a quick look at the different questions that are coming in. So NL's asking in the Q&A, when a client uses an old cipher and our server remove that 3-des cipher, will there be a new handshake or will a connection not work? That's a very good question. So the client will send a list of supported cipher suites. If they only support triple des and your server refuses to use triple des, then the connection will not work. Right? If the client supports other algorithms as well, then the server will simply pick one that isn't triple des and it will work. Right? So a good way of looking at it is you have to have at least one cipher in common between the client and the server for them to be able to be picked. Otherwise, it won't work. Right? That's what will happen. And then there'll be a message, an alert sent from TLS that says we haven't got a compatible cipher suite. Essay's asking a suspiciously complicated question. How can pre-master secret be a secret if it's composed of two publicly transmitted values? And that is the beautiful part of Diffie-Hellman key exchange, right? Diffie-Hellman key exchange is a mathematical construct that allows you to share two public messages and then learn a secret message, which is staggering still. And I know I've been teaching Diffie-Hellman for about 7 or 8 years, and I still think it's cool. I'm not going to go into the maths because that's for a different day, right? Or buy me a drink down the pub and we'll talk about it. But what I would say is that there are public values that are sent in the clear, but there are also private values that are very important that are kept behind, right? And those help with the mathematics of it, right? That's basically how it works. AP's said both client public and server public keys are sent unencrypted because they have not yet been encryption. There we go. So same question, right? The nature of Diffie-Hellman is that when you send those public values, you combine them with some secret values that you both have, and then they become a shared pre-master secret. If you'd like to learn more about Diffie-Hellman, I have done some videos on it, actually, and I also do another encryption course. But it does require some mathematical knowledge to really understand how it works. Right? It's worth doing, but just to bear that in mind. All right. So let's just, before we look at an exercise, let's just nod to TLS 1.3. Now, I expected in some sense TLS 1.3 to be more popular now than it is, in the sense that I assumed that everyone would just move straight away to TLS 1.3. Now, I think what's happened really is compatibility reasons. Old hardware doesn't know how to send 1.3 messages. And so, although it is meant to be backwards compatible, that has not really proven to be the case, perhaps. And so, I think that's one of the reasons why we're not seeing quite so much as we used to. Nevertheless, if you go to a modern website like Amazon or Google, you'll probably find you're using TLS 1.3 with any kind of modern browser. What are the differences? Well, there's major handshake improvements. Mostly, it's much, much faster than it was before. I mean, it didn't look slow from what we were just saying before, but it's much faster. All ciphers have been removed except for modern AEAD ciphers. So in answer to NL's question about triple DES is not enabled in TLS 1.3. If you want to support 1.3, you have to be able to talk either AES or char-char-20. Right? Those are the two. So there's no other ciphers at all. Whereas in 1.2, it was somewhat down to the server not to mess up their configuration to accidentally use the wrong cipher. The key exchange and authentication has been separated from the ciphers. It just makes it more modular and easy to configure. So what that means is that your cipher suite won't have ECDHE and RSA written in it. It will just be AES. And then the information on the key exchange and the authentication are sent separately as extensions. Right? It's an implementation issue more than anything else, really. Not hugely important. Much wider use of extensions for things like that. And finally, there's a neat trick called zero round trip time resumption, which I'll talk about in a moment. So let's look now at the difference between the two handshakes. You'll see that there are a lot of similarities, but they're a little bit different. Right? And the reason they're different is because basically TLS 1.3 assumes that we're going to be doing things in a certain way because that's what everyone does, and take some shortcuts. That's the idea. So if you look at the top of this, these here are, if I draw my little arrow, those are extensions, right? So these are additional information beyond the things that are normally held in a client hello. Now, the reason that TLS 1.3 exists is because it became so common just to use elliptic curve Diffie-Hellman that it kind of made sense to just get on and use elliptic curve Diffie-Hellman instead of always sending these hello messages where you always agree the exact same protocol you did last time. Right? So you don't send client hello, server hello, and then do the Diffie-Hellman. You just get straight on and do it. So you send the client hello, but in the client hello, you also send your public Diffie-Hellman key, right? And any supported signature algorithms to get ahead of the game, shall we say. The server can then respond with their public key for Diffie-Hellman, at which point encryption can already begin. So you can encrypt the extensions, the certificate verification signature, and the finish message in one go. And they can be built in, as you know, into the same record in the same IP packet. You can just literally fire off the entire conversation in one go. Now, it might be the case that maybe the server isn't happy using that particular Diffie-Hellman, in which case they would have to send a hello retry request, and you would, in essence, go back and do a normal TLS 1.2, right, where you both agree on something and you carry on. But 99.99% of cases, you're all going to be doing the same thing anyway every time, because most websites and browsers operate in the same way. And so you can save yourself a huge amount of time doing this, and it's also more secure because you have things that are encrypted now that weren't encrypted before. So it's better. The client can then verify the certificate from the certificate and certificate verify messages. They can send theirs if they need to, and they can get straight on with some finished and application data. So how good is this? Well, if we go back to our TLS 1.2 connection, notice that we go from the client to the server. That's one message. Then server hellos back to the client. And then the change type split and finishes back to the server, and then back to the client. So before we've sent any application data, we've had to make 2 round trips. We've gone client to server and back 2 round trips. Right? Now, if you're 400 milliseconds or half a second away across the other side of the world from the server, it's at least a second to finish this conversation. That's not a disaster, I should add, but it's worth bearing in mind. People don't like to wait for websites very long. TLS 1.3 is 1 round trip. If I just unhide it again, it's client to server and back, and we're good. And the application data is on the last. It's sent a whole pair of messages sooner than it was in TLS 1.2. So it's literally half as long, the handshake. Much, much faster. Really, really good. At the cost that it breaks compatibility with some other stuff, right? So, it's not always trivial to use. But it is better. If you can support 1.3, it's marginally faster. For most internet use, you're not going to notice a difference because a lot of web loading is after TLS and just general slowness, right? Because people are packing too much JavaScript in with their websites and so on. But it does make a little bit of difference every time you go on a website. The other thing that this allows is something called 0 round trip time resumption. Right now, this is perhaps the neatest thing that TLS 1.3 does. So imagine a situation where I've just been on a server half an hour ago, and I went to a website, and then I'm about to click a button on that website. We don't want to have to do a whole nother handshake only for me to send an HTTP GET request and then an HTTP response, right? Well, maybe I went on the website 2 hours ago and I want to go back on the website, but I want to get cracking and making HTTP requests. I don't want to wait. I can actually send, suppose the server has sent me some kind of pre-shared key material, right, during any conversation a little while ago, I can send that pre-shared key information here as part of my client hello and immediately encrypt application data with it. So this application data here is encrypted using the pre-shared key, which the server can then decrypt. And then the server can do the normal hello at the same time, but can also send application data here in the first round trip, right? So this is literally the minimum amount of time possible to get an encrypted connection. So suppose that first application data was an HTTP GET, there could be an HTTP response buried in the server hello, basically, or in the finish message, or just after, and that massively speeds this up. Right? Now, again, this is not as a client, or as a consumer, you're not going to see a huge difference here. But if you're visiting a website a lot, this is going to save a huge amount of time. Or for servers communicating, it just reduces the number of messages sent back and forth. Right? If you're a server, with millions of connections, a web server, this is going to save you some time. Right? Now, the only downside of this is that this is actually not a pre-shared key. It's an index. It's like a number that is like a client ID, basically, that allows the server to find whichever key it was. The thing to remember is that key could have been broken in the time between when it was first shared and when it was used. Right? That's true of a lot of cryptography. The longer you leave a key, exactly, is there a timeout? Yes, there will be a timeout set up in the server. I would say half an hour probably, but it will depend on the server's configuration, maybe 24 hours. Not longer than that would be my guess. Technically speaking, the pre-shared key could be broken. So what you would normally do is reserve this 0 round trip time approach for simple, insecure stuff like HTTP GETs and things like this. You wouldn't want to start doing HTTP post with personal data or doing any kind of server configuration change based on the early data because the key might have been broken, right? That's quite important. So just bear that in mind. You can serve data in your initial application data, but for proper requests, you would have to do the full key share and then go from there. Okay. AP's asking, HTTPS is a stateless protocol. How come a single handshake at the start of a request maintains an encryption state? Good question. HTTPS is not stateless. HTTPS or TLS is not stateless. It has a sequence number associated with each message, and each party, the client and the server, will hold information on the other one, right? The underlying HTTP that's being sent within that connection, that is still stateless. Right? So they are not related in some ways, which is why I think HTTPS is a slightly confusing term, because you're basically you've created a tunnel of TLS within which you're sending stateless HTTP, but they're not, you could replace one of them if you wanted to. Okay, so they're not absolutely intrinsically linked like that. TLS, MW is asking, does TLS work with all cryptography, civilian and military, or does military have a different protocol? That is an excellent question, and one I'm not sure I can answer off the top of my head. I don't believe there probably are military protocols for some communications on battlegrounds and things, sure. But, people in the NSA will just use the web like everyone else, and they will send messages using TLS because it's perfectly good. And at the end of the day, TLS is as good as the cipher it's using, something like AES, and these are acceptable ciphers to government agencies, for example, in the United States. So, yes, they won't have any problem using these. They might use different protocols for example, messages sent between a plane and the base station or something like that. What that protocol is, I couldn't tell you. All right, so I've talked for too long, so apologies for that. Let's have a go at an exercise, and maybe you'll learn, hopefully, a little bit more about how it actually works in practice. So depending on whether you like Java or Python best, and if you don't like either, leave some feedback in the questionnaire at the end saying, implement it in this language, please. But then I have to learn all these other languages. What this is, in exercise 1, you'll find an SSL client and an SSL server. Now, I've called them SSL because that's the naming convention in code, and it would get confusing otherwise. The server is already finished. If you look at the code for the server, it's already implemented. If you run that code, it will start listening on a port. What you then need to do is alter the client to successfully connect to the server, and there's instructions in the README on how to do that. You can then, if you have time, fiddle about with cipher suites and protocol parameters, depending on whether you want to or not. Right? Once you actually connect, the client will send a little bit of data to a server and get something back, just to show you that it works. So what I usually do during exercises, I'll go off camera, so I'm not disturbing people and sitting here like a bit of a lemon. But I will still be here, and I will be answering any questions you have in the Q&A or in the attendee chat. And what we'll do is we'll work on this for a little bit, and then perhaps we'll go for a break before we go into the next bit, where we're going to talk about PKI, or public key infrastructure. So